So, asking for ketones and aldehydes. What's the ketone and aldehyde this comes from, and what's the protecting group diol? So again, a good numbering system will really be helpful here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Go that way. A little different than one. What you need to look for is the carbon bonded to oxygen. 2 times, right? Because you're trying to find out, well, which carbon is acetyl bond O, is the carbonyl. So you got to find that carbon. That's what's going to tell you is the carbon and the carbonyl. And so for this first one, for A, the carbon that is bonded to 2 oxygens is carbon 1. In our example B, the carbon that's bonded to 2 oxygens is carbon 4. Carbon 4, just to remind ourselves, is also bonded to 2 hydrogens. Carbon 1 is bonded to 2 carbons. So we were looking for that carbon, the carbonyl, but it had to be the one that is bonded already to oxygen twice. Okay. So that means this first one, that is the ketone. That's carbon 1. Number our carbons, 2 our atoms, 3, 4, 3. Oh gosh, 2, 3, 4, and 5. All right, there's 1. So you see that protecting group. Now for the other one, 4 had 2 hydrogens on it, so it's this. It's an aldehyde. That's 4. So the alcohol had to be that. 1, 2, 3, 5, 6. Right? The key to all these problems is identifying the carbon that's bonded to the two oxygens. Right? Now again, some people ask this good question about why do we do this, right? So this actually changes the reactivity quite a bit. Show me your pi bonds. What do we know about pi bonds? Do they have as much orbital overlap as a sigma bond or less? More or less? A pi bond has less orbital overlap, right? Sigma bonds, right? So pi bonds are more reactive, or we say weaker is a term, right? So the reason we do this is because this actually makes this carbon less reactive, right? It's more reactive when it's a sigma and a pi versus 2 sigmas, right? So it takes something and makes it less reactive. It's a protecting group, right? And you saw a couple examples where it protected an aldehyde in the presence of a ketone, right? We talked about aldehydes are less reactive than ketones. But what if I want to react with a ketone? Well, then I need to protect that aldehyde because pretty much everything that reacts with a ketone reacts with an aldehyde first. So this is a good way, right? If you had a ketone and an aldehyde in your molecule, protect the aldehyde, put one of these things on it, these acetals, and then you can do some chemistry on your ketone, wherever you want. Then you can unprotect your aldehyde and you get your aldehyde back. Right? So that's kind of the why we do these things. So a question like this has come up. So you know how to make an imine, right? You know how to make an imine. This is an enamine, excuse me. This is an enamine. So I number my atoms there. 1, 2, 3. Enamine. And this is from a secondary amine and a ketone or aldehyde that has alpha CHs. Right? It has alpha CHs. So a couple things. I would always put this H3O plus on the top. This is a solvent, I put that on bottom. But we're seeing it differently, so there you go. So hopefully you recognize this, similar to how we just recognized those acetals, that carbon 2 was where the carbonyl was at. There's a ketone there. So I'm not going to go through the mechanism right now. I think we've done the mechanism. But if I go back one step, right, maybe I'll go through the mechanism too. You should be able to look at that and say, oh, that was this. Three, two, one. But you can look at this enamine and immediately draw these 2 things. A secondary amine and a ketone in this case. So you should be able to do that. Now, on this question, the added part was, okay, let's say you have this, and if you have H plus still floating around, right, the amine's actually going to react with that. So I think one of these questions where, at the end of the day, I care that you know these two things, but they also want you to recognize that you're also generating this, which, okay, okay, but that's neither here. I think it's still it's another source of H plus because this H could just fall off as easily too. Do I need to go through the mechanism? All right, same ketone. Both of them are under acidic conditions, right? H plus is the same as HCl. I would always put these things on the bottom. That's just my preference. Things like this that are probably solvents would go on the bottom. I want them there. What they're asking you here in this one, I guess, sorry, I need to add this in. This is saying one equivalent. So they're basically what you're doing is you're taking a ketone and you're going to turn it into an acetal or a hemi-acetal based on the number of equivalences of alcohol you have. So we've gone through this mechanism, but if you see two equivalences, right, you know you're going to make water, you're going to lose this, and you're going to add two of these there. So again, not to belabor the mechanism, right, water, and then this is, of course, a catalyst. Right, you'd make that acetal. If there's only one equivalent, which, I don't know how you can control that, but sure, you're making this. And of course, this is also a catalyst. But if you see HCl, that's just like H plus Cl minus. All right, so in theory, controlling the equivalences you can get these kind of things. In theory. So this is an acetal, this is a hemi-acetal. So that helps with a couple of those problems I did.